Max Planck was born on April 23, 1858, in the northern German city of Kiel, a place marked by quiet streets, old architecture, and a culture steeped in scholarship and discipline. He came into the world during a period of immense scientific and intellectual activity in Europe, where the Industrial Revolution was reshaping society and natural philosophy was evolving into the modern science we know today. From the very beginning, Planck's environment played a subtle yet powerful role in shaping his mind. His father, a professor of law at the University of Kiel, was a man of intellect, deeply committed to logic, moral reasoning, and rigorous thought. His mother, equally devoted to education and the arts, nurtured a sense of discipline and appreciation for the beauty of structured ideas. In this household, young Max grew up immersed in conversation, debate, and observation, learning from an early age that understanding the world required both curiosity and patience. Even as a child, Max demonstrated a remarkable aptitude for intellectual pursuits. Unlike many children who are drawn to simple amusements, Planck was captivated by the hidden patterns in nature. He noticed the way light streamed through windows at certain angles, the way heat seemed to spread unevenly across surfaces, and the subtle rhythms in music and poetry. His curiosity was not superficial. He asked probing questions that reflected a desire to understand causality, not just outcomes. Teachers in his early schooling recognized this unusual inclination. While other students memorized facts and equations, Planck seemed to seek the underlying principles that governed those facts. His mind was drawn to the laws that connected cause and effect, to the invisible structures beneath everyday phenomena. Planck's formal education began in earnest at the local gymnasium, where the curriculum was rigorous, emphasizing mathematics, classical languages, and natural sciences. It was here that he encountered the foundations of physics, first through mechanics, then through the study of heat, light, and electromagnetism. While many of his peers found the subjects abstract or challenging, Planck embraced them with a quiet intensity. He would spend hours poring over textbooks, attempting to understand not only how equations worked, but why they worked. He experimented mentally, imagining hypothetical scenarios, drawing diagrams in the margins of his notebooks, and attempting to reconcile theoretical principles with observable reality. This method of internal experimentation became a hallmark of his later work, allowing him to explore ideas before formalizing them mathematically. Family influence continued to shape Planck's intellectual trajectory. His grandfather, a respected mathematician and physicist, had established a lineage of scholarship that imbued the family with a sense of duty to contribute to human knowledge. Stories of discovery and academic rigor were part of Planck's upbringing, presented not as abstract tales, but as living examples of how inquiry could illuminate the mysteries of the universe. This environment instilled a dual sense of responsibility and possibility in him, a belief that human reason could probe nature's secrets, and an understanding that such pursuits required patience, perseverance, and moral integrity. By his teenage years, Planck's engagement with physics had moved beyond mere curiosity. He was particularly drawn to the emerging field of thermodynamics, which sought to explain heat, energy, and the movement of matter. The laws of energy conservation and the mysterious behavior of entropy fascinated him. He devoured works by scientists such as Rudolf Clausius and Lord Kelvin, seeking to understand the fundamental principles that underpinned thermal phenomena. Planck's approach was not purely academic. He visualized molecules, imagined their collisions, and contemplated the invisible processes that produced observable heat and light. He began to develop the habit of thinking about problems from first principles, a method that would later allow him to challenge entrenched scientific dogmas. During these formative years, Planck also exhibited a deep appreciation for music, which influenced his scientific perspective. He became an accomplished pianist, finding solace and inspiration in the structured yet expressive nature of musical composition. Music taught him about patterns, harmony, and the interplay of discrete elements to produce a coherent whole. This sensitivity to structure, rhythm, and subtlety resonated with his later insights into the quantized nature of energy. Just as a melody is composed of individual notes arranged with precise timing, Planck would come to see energy as composed of discrete packets, an intuition that music had perhaps helped nurture. Planck's transition from curiosity to formal scientific pursuit became evident when he enrolled at the University of Munich at the age of 18. There, he studied physics under some of the most prominent scholars of the time, immersing himself in lectures on mechanics, electromagnetism, and thermodynamics. Munich exposed him to the forefront of experimental and theoretical work, and Planck absorbed knowledge with a combination of humility and determination. While some students focused on rapid advancement or academic prestige, Planck's approach was methodical. He preferred to understand deeply, building a foundation that would allow him to innovate rather than merely replicate existing ideas. His professors noticed his extraordinary analytical abilities, and he quickly developed a reputation for diligence, insight, and the ability to see connections that others overlooked. Even as a university student, Planck was not content to limit himself to lectures and textbooks. He conducted independent investigations, often grappling with questions that seemed intractable. The nature of heat radiation, the distribution of energy, and the behavior of electromagnetic waves were areas where he sought clarity. He wrestled with paradoxes, spending countless hours pondering the inconsistencies between theory and experiment. These struggles honed his resilience, teaching him that scientific discovery often requires patience, persistence, and a willingness to confront uncertainty without becoming discouraged. In many ways, these early challenges foreshadowed the revolutionary breakthroughs he would later achieve. Planck's personal characteristics during these early years, intellectual rigor, humility, perseverance, and curiosity, were as important as his formal education in shaping his scientific destiny. He displayed a capacity for long-term thinking, for pursuing questions whose answers might take years or decades to emerge. Unlike some contemporaries who sought immediate recognition or practical applications, Planck was motivated by a profound desire to understand nature's laws at their most fundamental level. This mindset allowed him to approach problems with an open yet disciplined perspective, balancing imagination with analytical precision. His early fascination with physics was also intertwined with philosophical reflection. Planck was deeply aware that the study of nature was not merely a technical endeavor, but a profound exploration of reality itself. He read widely, engaging with philosophical texts that contemplated causality, determinism, and the limits of human knowledge. These reflections influenced his scientific approach, instilling a sense of humility and a recognition that understanding nature is both a privilege and a responsibility. In his later years, Planck would often emphasize the moral dimensions of scientific work, but even as a young man, he understood that discovery was inseparable from ethical consideration, that the pursuit of knowledge carries obligations toward society and future generations. By the time he completed his formal studies in Munich, Planck had already developed the intellectual habits and moral grounding that would define his career. He was methodical in reasoning, imaginative in speculation, and unwavering in his commitment to truth. These qualities, nurtured through family influence, rigorous education, personal reflection, and early experimentation, provided the foundation for his later breakthroughs in quantum theory. The questions that had captivated him as a child about heat, energy, and the invisible structures of nature would continue to guide him throughout his life, ultimately leading to a discovery that would transform the very framework of physics. In looking back on Planck's early years, one can see the convergence of multiple forces: a supportive family environment, rigorous schooling, personal curiosity, exposure to contemporary scientific thought, engagement with music and philosophy, and an innate capacity for patience and perseverance. Each of these elements contributed to the formation of a mind capable of imagining the unimaginable. Planck did not merely absorb knowledge, he internalized it, questioned it, and prepared himself to extend it beyond the limitations of his time. This preparation was subtle and gradual, like the slow formation of a crystal lattice, with each experience and insight adding a layer of strength and complexity to his intellectual structure. By the end of this formative period, Max Planck was not yet the world-renowned physicist whose name would be immortalized in the constant that bears his name, but he was a thinker poised on the threshold of extraordinary discovery. He had cultivated a combination of curiosity, rigor, and moral reflection that would allow him to confront problems that others considered unsolvable. The seeds of quantum theory, which would one day shake the foundations of physics, were being sown in the quiet streets of Kiel, in the lecture halls of Munich, and in the reflective moments of a young man determined to understand the universe at its most fundamental level. It was this unique convergence of environment, education, and personal disposition that set Max Planck on a path to become the man who would unlock the quantum universe. As Max Planck matured, the foundations laid in his youth began to manifest more clearly in his approach to science. His early fascination with the hidden structures of nature, nurtured by family influence and formal education, evolved into a disciplined engagement with the scientific community. Planck's arrival at higher academic circles coincided with a period of profound transformation in physics. The late 19th century was a time of both confidence and uncertainty. Classical physics, founded on Newtonian mechanics and Maxwell's electromagnetic theory, seemed to explain almost everything, yet anomalies were beginning to surface that defied conventional reasoning. For Planck, these anomalies were not obstacles but invitations to explore deeper truths. During his years as a young scholar, Planck's focus increasingly turned to thermodynamics, particularly the perplexing behavior of heat radiation. He was captivated by the idea that energy, which seemed so continuous and smooth in the macroscopic world, might behave differently at microscopic scales. The problem of blackbody radiation, which involved understanding how objects emit energy in the form of light and heat, became a central preoccupation. Many established scientists had attempted to reconcile the observed spectral distribution with classical laws, only to encounter contradictions. Planck approached the problem with a combination of analytical rigor and creative intuition. Unlike some of his contemporaries, who were content with approximate solutions, he sought a deeper understanding of the principles governing energy exchange. What set Planck apart was not only his intellectual capacity, but his ability to engage with problems over extended periods without losing clarity or focus. While many researchers moved from topic to topic, Planck's curiosity was both persistent and patient. He spent countless hours in his study, performing calculations, revisiting experiments, and questioning assumptions. He would examine the work of predecessors and peers, analyzing their logic and methodology, while also imagining new possibilities that had not yet been considered. This patient, almost meditative approach allowed him to perceive connections that eluded others. It was the intellectual equivalent of walking a labyrinth slowly and deliberately, observing every turn and shadow before deciding on the path forward. Planck's personal life, while filled with the challenges common to many in that era, also shaped his scientific disposition. He experienced profound personal loss, including the untimely deaths of family members, which instilled in him a deep sense of the fragility of life and the enduring nature of ideas. These experiences fostered resilience, a quality that would prove essential when he later confronted the revolutionary implications of his own discoveries. Planck understood that the pursuit of knowledge often involves grappling with uncertainty and risk, and he approached his work with a balance of caution and courage. His intellectual perseverance was mirrored by moral perseverance, a steadfast commitment to truth that transcended personal ambition. By the mid-1880s, Planck had begun to make a name for himself within the academic community. His publications on thermodynamics and electromagnetic theory demonstrated a rare combination of analytical precision and innovative thought. He was respected not only for his technical competence, but also for his integrity and dedication to rigorous reasoning. Colleagues recognized that Planck was not seeking fame or accolades. He was driven by the pursuit of understanding. This reputation would later lend weight to his revolutionary ideas, ensuring that when he introduced the concept of energy quanta, the scientific community would take it seriously, even if it initially seemed counterintuitive. It is important to understand that Planck's approach to science was deeply philosophical as well as technical. He did not see equations merely as tools for prediction. He viewed them as reflections of the underlying order of the universe. For him, the study of physics was inseparable from the study of reality itself. He was influenced by thinkers who contemplated the nature of causality and the limits of human knowledge, and he sought to integrate this philosophical awareness into his scientific practice. This holistic perspective allowed him to approach problems with both analytical rigor and imaginative flexibility, a duality that would prove essential in the development of quantum theory. Planck's intellectual journey during these years was also shaped by the broader scientific community. He engaged with contemporary debates on the nature of light, energy, and matter, and he was attentive to the experimental results that challenged classical theory. He corresponded with leading scientists, attended conferences, and studied the work of pioneers such as Ludwig Boltzmann, whose statistical interpretation of thermodynamics deeply influenced Planck's thinking. While Boltzmann grappled with the probabilistic behavior of molecules, Planck began to see hints that energy itself might exhibit discrete behavior, a radical departure from classical continuity. This insight did not emerge overnight. It was the result of years of meticulous study, reflection, and mental experimentation. Planck's early experiments, though largely theoretical in nature, reflected a methodical process of hypothesis and verification. He would construct detailed mathematical models, test them against known experimental data, and refine his assumptions iteratively. This iterative process, combining intuition with rigorous calculation, allowed him to navigate complex problems that resisted simple solutions. He learned to tolerate ambiguity, recognizing that understanding often unfolds gradually through a series of incremental insights rather than sudden leaps. This patience, cultivated over years of disciplined inquiry, would become a defining feature of his scientific character. Another key aspect of Planck's early development was his ability to integrate multiple disciplines and perspectives. His appreciation for music, philosophy, and literature was not merely recreational, it enriched his scientific imagination. Music taught him about patterns, structure, and harmony, while philosophical reflection sharpened his awareness of conceptual subtleties and the limits of certainty. These influences allowed him to approach physics not merely as a set of equations, but as a dynamic interplay of principles, observations, and abstract reasoning. He developed an intuitive sense that the universe, at its most fundamental level, might operate according to rules that were both precise and discrete, a notion that would eventually crystallize in his quantum hypothesis. By the time Planck reached the threshold of his professional career, he had accumulated a wealth of intellectual resources. He had mastered classical physics, engaged deeply with thermodynamics and electromagnetism, and cultivated a disciplined yet imaginative approach to problem solving. He had endured personal hardships that strengthened his resilience, and he had absorbed philosophical and artistic influences that enriched his perspective. Above all, he had nurtured a profound curiosity about the hidden structures of nature, a curiosity that demanded answers beyond the conventional wisdom of his time. This combination of preparation, insight, and perseverance set the stage for one of the most transformative breakthroughs in the history of science. The significance of Planck's early intellectual formation cannot be overstated. It illustrates how the mind of a great scientist is shaped by a confluence of factors: familial environment, rigorous education, personal curiosity, resilience in the face of adversity, and exposure to both technical and philosophical thought. Planck's later work, which would revolutionize physics, was not the product of sudden inspiration alone. It was the culmination of decades of patient observation, reflection, and disciplined study. Each stage of his early life contributed to the development of a mindset capable of seeing beyond established paradigms, of imagining a universe in which energy is not continuous but quantized, and of daring to articulate a vision that initially seemed impossible. In reflecting on these formative years, one can also appreciate the subtle ways in which Planck's early experiences influenced his character as a scientist and as a person. His humility, integrity, and commitment to truth were cultivated alongside his intellectual abilities. He learned to approach problems systematically, to question assumptions without being reckless, and to pursue knowledge with both courage and caution. These qualities allowed him to confront the profound implications of his later discoveries without succumbing to hubris or sensationalism. Planck's early life, therefore, was not merely a prelude to his achievements. It was the essential foundation upon which his revolutionary contributions would be built. By the end of this period of early intellectual development, Planck was poised to make history. His curiosity about energy, heat, and the fundamental structures of matter had evolved into a disciplined and imaginative scientific practice. The stage was set for the emergence of the quantum hypothesis, a concept that would challenge the very foundations of classical physics and open a new chapter in human understanding of the universe. Every lecture attended, every experiment pondered, every philosophical reflection considered, and every note of music absorbed had contributed to the formation of a mind uniquely equipped to recognize and articulate a truth that others could not yet see. Max Planck's early life reminds us that scientific genius is rarely spontaneous. It is forged through years of preparation, guided by curiosity, shaped by environment, and strengthened by resilience. It teaches us that the seeds of revolutionary discovery are often planted in quiet moments of observation and reflection, nurtured by discipline and intellectual integrity. Planck's journey from a curious child in Kiel to a young scholar in Munich was marked by an unwavering pursuit of understanding, a dedication to rigorous thought, and an enduring fascination with the invisible laws governing the natural world. These formative experiences would ultimately enable him to unlock the quantum universe, altering forever how humanity perceives the fundamental nature of reality. As Max Planck matured in his scientific career, the mysteries of energy and heat became more than abstract puzzles. They became an urgent calling. In the late 19th century, physics was at a crossroads. Classical mechanics and electromagnetism seemed to explain the world with remarkable precision. Yet a small but growing body of experimental evidence hinted at a deeper layer of reality that defied conventional understanding. Among these challenges, one particular problem captivated Planck: the behavior of blackbody radiation. A blackbody is an idealized object that absorbs all light and heat falling upon it and re-emits energy in a spectrum determined by its temperature. Physicists of the time were perplexed because classical theory, based on the laws of thermodynamics and electromagnetism, could not accurately describe the observed radiation spectrum. At low frequencies, the predictions seemed reasonable, but at high frequencies, classical theory suggested an ultraviolet catastrophe, a divergence that implied infinite energy emission, a conclusion that was clearly impossible. Planck approached this problem with a methodical combination of theoretical rigor and intellectual daring. He recognized that resolving the discrepancy required not only careful analysis of existing data, but also a willingness to reconsider the fundamental assumptions of physics. Unlike some of his contemporaries, who dismissed anomalies as experimental errors or minor oversights, Planck treated the blackbody radiation problem as a profound challenge. He was convinced that nature operated according to precise, discoverable laws, and that the apparent contradictions were clues to a deeper truth. Planck's mindset reflected both humility and audacity. Humility in acknowledging the limitations of current theory, and audacity in imagining that reality might behave in ways never before conceived by classical physics. To tackle the problem, Planck began by analyzing the experimental data on blackbody radiation, paying close attention to the work of contemporary physicists such as Heinrich Rubens and Ferdinand Krölbaum. Their meticulous measurements of radiation intensity at different temperatures provided a detailed empirical landscape. Planck immersed himself in this data, studying the curves, noting patterns, and attempting to reconcile them with theoretical predictions. His early attempts relied on classical methods, applying thermodynamics and Maxwellian electromagnetism to derive formulas for the emission spectrum. While these methods yielded partial success at lower frequencies, the predicted intensities at higher frequencies were catastrophically wrong, diverging to infinity. Classical physics, in its continuous and deterministic framework, seemed incapable of explaining the behavior of energy at the microscopic level. It was during this process of persistent engagement that Planck arrived at a radical insight. If classical assumptions were failing, perhaps a fundamental rethinking of energy itself was required. Planck hypothesized that energy could not be exchanged in arbitrary amounts, as classical theory assumed. Instead, he proposed that energy was emitted and absorbed in discrete, quantized packets, which he called energy elements, or quanta. Each quantum of energy was proportional to the frequency of radiation, introducing a constant that would later become universally known as Planck's constant. This simple yet profound idea, that energy is fundamentally discrete rather than continuous, provided a framework that could reconcile theory with observation. It was a departure from centuries of continuous thinking, a bold leap into a conceptual realm that no one had dared to explore before. Planck's quantum hypothesis was not immediately intuitive, even to himself. He initially regarded it as a formal mathematical construct, a convenient tool to fit experimental data, rather than a literal description of reality. Yet over time, he began to appreciate the deeper implications. The universe, at its most fundamental level, might operate according to rules that were inherently granular. The behavior of heat, light, and radiation suggested a universe composed not of smooth flows of energy, but of discrete, countable units. This realization was both exhilarating and unsettling, challenging centuries of classical assumptions about continuity, determinism, and the smoothness of physical processes. The formulation of the quantum hypothesis was a painstaking process. Planck derived a formula that accurately described the observed blackbody spectrum at all frequencies. By assuming that energy could only be exchanged in integer multiples of the basic quantum, he achieved a precise match with experimental data. This formula, now known as Planck's radiation law, represented the first major breakthrough in quantum theory. It solved the ultraviolet catastrophe, provided a consistent theoretical framework for thermal radiation, and laid the foundation for the modern understanding of atomic and subatomic processes. Planck's approach exemplified the interplay between empirical observation and theoretical creativity, careful attention to experimental data, coupled with imaginative reformulation of fundamental principles. Even as he developed this revolutionary idea, Planck remained cautious about its broader implications. He was aware that proposing quantized energy challenged deeply entrenched scientific beliefs, and he initially presented it as a mathematical convenience rather than a radical new view of nature. His humility, a defining characteristic throughout his career, led him to emphasize that the quantum hypothesis was grounded in observation and necessity, not speculative philosophy. Planck's careful presentation allowed the scientific community to take his ideas seriously, even as many struggled to accept the radical conceptual shift implied by energy quanta. The intellectual environment of the time both facilitated and constrained Planck's work. The late 19th century physics community was highly rigorous, with an emphasis on mathematical precision and empirical validation. While this rigor encouraged careful analysis, it also created resistance to ideas that appeared to violate established norms. Planck navigated this environment with a combination of subtlety and perseverance. He presented his findings in respected journals and conferences, carefully framing the quantum hypothesis as a solution to an urgent problem rather than a philosophical revolution. This strategic approach helped his ideas gain traction, while allowing him time to refine his thinking and explore the implications of quantized energy. Planck's work on blackbody radiation had immediate scientific significance. It resolved a long-standing theoretical problem and provided a consistent framework for understanding thermal emission. But its true revolutionary potential lay in the doors it opened for future discoveries. By introducing the concept of quantized energy, Planck inadvertently laid the groundwork for the quantum mechanics revolution. Subsequent scientists, inspired by his insights, applied the quantum principle to light, electrons, and atomic structure, leading to groundbreaking discoveries by Albert Einstein, Niels Bohr, and many others. Planck's initial hypothesis, motivated by a specific problem in thermal radiation, became the seed for an entirely new paradigm in physics, transforming the way humanity understands the microscopic and subatomic worlds. The process by which Planck developed his quantum hypothesis also illustrates the nature of scientific discovery itself. It was not a sudden flash of genius, but the result of sustained observation, careful reasoning, and imaginative experimentation. He combined meticulous analysis of experimental data with creative reformulation of theoretical principles. He tolerated uncertainty, embraced complexity, and patiently pursued insights that required years of reflection to emerge. This methodological patience, coupled with a willingness to question fundamental assumptions, exemplifies the intellectual discipline that distinguishes transformative scientific thinkers. Planck's quantum hypothesis also carried profound philosophical implications. By proposing that energy is quantized, he challenged the classical notion of continuity and determinism. The microscopic world, he suggested, is governed by discrete events, probabilistic exchanges, and fundamental limits on the divisibility of energy. This view introduced a new lens through which to understand nature, one that accommodates uncertainty, granularity, and the subtle interplay between observation and physical reality. Though Planck himself initially treated the quantum concept as a formal tool, the idea resonated deeply, eventually reshaping philosophical and scientific notions of causality, measurement, and the structure of the universe. The reception of Planck's hypothesis was mixed, reflecting the tension between revolutionary ideas and established scientific tradition. Many contemporaries found the notion of quantized energy difficult to reconcile with classical physics. Some regarded it as a temporary mathematical trick, while others saw the potential for a profound shift in understanding. Over time, however, as further experimental evidence accumulated and additional theoretical work extended Planck's insights, the quantum hypothesis gained acceptance. What began as a solution to a technical problem in blackbody radiation evolved into the cornerstone of quantum mechanics, demonstrating how careful attention to empirical anomalies, coupled with creative conceptual leaps, can transform the trajectory of science. Planck's personal approach to this problem also reveals much about his character. He balanced bold intellectual innovation with humility, rigorous analysis with imaginative speculation, and technical precision with philosophical reflection. He understood that discovery carries responsibility, that revolutionary ideas must be communicated with care, and that the pursuit of truth often requires patience and perseverance. These qualities not only enabled him to solve the blackbody radiation problem, but also positioned him to influence generations of physicists who would expand upon his work, ultimately shaping the modern understanding of matter, energy, and the quantum world. Through the lens of blackbody radiation, one can see the emergence of Planck's unique scientific vision. He was a thinker who refused to be constrained by established doctrine, yet he grounded his imagination in observation and mathematical rigor. He recognized patterns that others overlooked, challenged assumptions that others took for granted, and pursued insights that required both patience and courage. The quantum hypothesis, born from the seemingly technical problem of thermal radiation, exemplifies the intersection of intellect, creativity, and perseverance. It is a testament to the power of disciplined curiosity, the willingness to embrace uncertainty, and the courage to imagine a universe that behaves in ways previously unthinkable. Planck's work during this period also underscores the interconnectedness of scientific progress. The resolution of blackbody radiation was not an isolated achievement. It relied on the cumulative knowledge of prior generations, from classical thermodynamics to Maxwellian electromagnetism, and it paved the way for future breakthroughs. Planck stood at the nexus of tradition and innovation, respecting established knowledge while daring to extend it into uncharted territory. This delicate balance, between reverence for what is known and openness to what is possible, characterizes much of his scientific legacy. As Part A of the exploration of Planck's work on blackbody radiation and the quantum hypothesis comes to a close, it is evident that this phase of his career represents more than a technical achievement. It exemplifies the qualities of a pioneering mind: curiosity, rigor, patience, imagination, humility, and courage. Through his meticulous analysis of thermal radiation and his daring introduction of quantized energy, Planck not only solved a perplexing scientific problem, but also laid the conceptual foundation for an entirely new understanding of the universe. The quantum hypothesis, initially a response to empirical anomalies, would grow into a revolutionary framework, forever altering humanity's comprehension of the microscopic world and revealing the universe as a far more intricate and mysterious place than classical physics could describe. As Max Planck's quantum hypothesis began to take shape, he became increasingly aware of the revolutionary nature of his idea. Although initially he presented quantized energy as a mathematical convenience, the more he pondered it, the more he recognized its profound implications. Energy, previously thought to be a continuous flow, appeared instead to occur in discrete packets. This realization unsettled many classical assumptions, but also opened a doorway to a new understanding of the universe. Planck's careful examination of the blackbody problem revealed that nature, at its most fundamental level, operated according to principles that defied intuition, yet provided a precise and predictable framework when analyzed mathematically. The derivation of Planck's radiation law was a monumental intellectual effort. He combined the principles of thermodynamics with statistical mechanics, a relatively young branch of physics, to create a formula that accurately described the observed spectrum of blackbody radiation at all temperatures. This formula required the introduction of a fundamental constant, later named Planck's constant, which quantified the smallest possible unit of energy exchange for a given frequency. The elegance of the solution lay not only in its accuracy, but also in its simplicity. A single hypothesis, supported by careful mathematics, resolved a problem that had confounded the scientific community for decades. Planck's breakthrough did not occur in isolation. He was deeply influenced by the work of earlier scientists, particularly Ludwig Boltzmann, whose statistical approach to thermodynamics provided a framework for understanding energy distribution at the molecular level. Planck extended these ideas, recognizing that if energy exchanges were quantized, the statistical methods of Boltzmann could explain the observed radiation spectrum. By blending experimental data, thermodynamic reasoning, and statistical analysis, Planck demonstrated that energy quantization was not an arbitrary assumption, but a necessary condition for consistency with observation. This interplay of theory and experiment exemplified Planck's methodical approach. He allowed empirical evidence to guide theoretical innovation, ensuring that his ideas were grounded in reality while simultaneously extending the boundaries of understanding. The introduction of quantized energy challenged deeply held beliefs about the continuity of nature. Classical physics, built upon Newtonian mechanics and Maxwellian electromagnetism, had assumed that energy could be divided infinitely and transferred smoothly. Planck's hypothesis suggested otherwise. At microscopic scales, energy is discrete, exchanged in indivisible units. This insight marked a fundamental departure from centuries of continuous thinking and laid the groundwork for the probabilistic framework of quantum mechanics. The notion that energy is quantized would soon find resonance in other areas of physics, from the photoelectric effect to atomic spectra, eventually revolutionizing the entire field. Planck's approach to the quantum hypothesis was marked by a unique combination of intellectual courage and methodological caution. He understood the radical nature of his idea, but carefully presented it as a solution to a specific experimental problem, rather than a sweeping challenge to classical physics. This strategic restraint allowed the scientific community to engage with the hypothesis without dismissing it outright. Planck published his findings in respected journals and presented them at conferences, emphasizing the empirical success of his formula rather than the philosophical implications. By doing so, he ensured that his ideas would be taken seriously, even as many struggled to grasp their full significance. The reception of Planck's quantum hypothesis was initially mixed. Some physicists viewed it as a clever mathematical trick, a formal device to fit experimental data, while others sensed its potential to redefine fundamental concepts. Albert Einstein, in particular, would soon extend Planck's ideas to explain the photoelectric effect, demonstrating that light itself is quantized. Niels Bohr applied the concept to atomic structure, developing a model in which electrons occupy discrete energy levels. These extensions highlighted the generative power of Planck's insight. From a solution to a technical problem in thermal radiation emerged a conceptual framework capable of explaining a wide range of previously mysterious phenomena. Planck's meticulous nature and disciplined work ethic were critical in navigating the uncertainties inherent in revolutionary science. He was not a flamboyant or impulsive theorist. He approached problems with careful reasoning, double-checking calculations, and examining every assumption. His persistence in confronting the blackbody radiation problem, often through repeated iterations of analysis and calculation, exemplifies the patience required for true scientific innovation. This methodical approach ensured that his conclusions were robust and credible, allowing the quantum hypothesis to gain acceptance gradually even as it challenged deeply ingrained scientific norms. The philosophical implications of Planck's work extended far beyond physics. By introducing the concept of quantization, he challenged deterministic notions of the universe. In classical physics, the world was continuous, predictable, and governed by exact laws. Quantum theory, beginning with Planck's insights, suggested a universe where discreteness, probability, and uncertainty play fundamental roles. Planck himself was cautious in interpreting these broader implications, but the intellectual seeds he planted would later blossom into a profound rethinking of reality, influencing not only science but philosophy and epistemology. Planck's personal qualities, his humility, patience, and dedication to truth, were instrumental in the development and reception of his ideas. He faced a paradox common to revolutionary thinkers: the need to propose radical concepts while maintaining credibility within a conservative scientific community. Planck navigated this tension with remarkable balance. He was steadfast in his commitment to empirical accuracy and methodological rigor, yet open-minded enough to entertain ideas that challenged classical assumptions. This balance allowed him to introduce the quantum hypothesis in a manner that was both innovative and defensible, ensuring that it would serve as a foundation for further exploration rather than a fleeting curiosity. The implications of the quantum hypothesis for science and technology were profound. By establishing that energy is quantized, Planck opened the door to a new understanding of atomic and subatomic processes. The theory would eventually underpin the development of semiconductors, lasers, nuclear energy, and modern electronics. Every contemporary technological marvel, from smartphones to quantum computers, traces its conceptual lineage back to Planck's insight. Beyond technology, the quantum hypothesis reshaped scientific thinking itself, challenging assumptions, expanding the scope of inquiry, and demonstrating that empirical anomalies, when approached with creativity and rigor, can lead to transformative breakthroughs. Planck's work also illustrates the cumulative and collaborative nature of scientific progress. He built upon the foundations laid by predecessors, integrated contemporary experimental data, and inspired subsequent generations to extend his insights. The quantum hypothesis did not emerge fully formed but evolved through careful analysis, iterative refinement, and dialogue with the scientific community. Planck's contribution was not merely in proposing quantized energy, but in creating a framework that could accommodate and stimulate further discovery, exemplifying the dynamic interplay between individual insight and collective advancement in science. The resolution of the blackbody radiation problem highlights the importance of curiosity, observation, and analytical rigor in scientific discovery. Planck's journey from puzzling experimental data to the introduction of energy quanta demonstrates how persistent engagement with anomalies can yield revolutionary insights. He did not seek fame or acclaim, he sought understanding, yet his insights transformed the scientific landscape, revealing that even the most perplexing phenomena can yield to careful reasoning, imaginative thinking, and disciplined investigation. Planck's work on blackbody radiation and the quantum hypothesis also exemplifies the interplay between mathematics and physical reality. He demonstrated that abstract mathematical constructs, when carefully aligned with empirical data, can reveal deep truths about the natural world. The quantization of energy was initially a theoretical tool, yet it accurately described observable phenomena, illustrating the profound connection between mathematical reasoning and the behavior of nature. This principle continues to guide modern physics, from particle theory to cosmology, reinforcing Planck's enduring influence on the scientific method itself. As the narrative of Part B unfolds, it becomes clear that Planck's quantum hypothesis was more than a technical solution, it was a conceptual revolution. By daring to imagine that energy could exist in discrete units, he laid the foundation for quantum mechanics, one of the most transformative frameworks in the history of science. His approach, grounded in observation, guided by careful reasoning, and tempered by humility, demonstrates how extraordinary scientific discoveries often emerge from the intersection of rigorous analysis and imaginative speculation. Planck's exploration of blackbody radiation also underscores the importance of confronting contradictions. Classical physics had reached the limits of its explanatory power, yet instead of abandoning the problem, Planck embraced it as an opportunity to rethink fundamental assumptions. This mindset, viewing anomalies as opportunities rather than obstacles, is a hallmark of groundbreaking science. It illustrates how curiosity, persistence, and intellectual courage can transform a seemingly intractable problem into a gateway for profound insight. By the conclusion of this period, the quantum hypothesis had taken firm hold in theoretical physics. It resolved the ultraviolet catastrophe, provided a predictive framework for thermal radiation, and signaled a new era in scientific understanding. Planck had not only solved a specific experimental problem, but it also set in motion a revolution that would redefine the nature of energy, matter, and the microscopic universe. The journey from puzzling data to quantum insight exemplifies the process of scientific discovery, observation, analysis, hypothesis, and iterative refinement, guided by creativity, discipline, and intellectual integrity. The story of Planck's quantum hypothesis is also a testament to the enduring value of patient, methodical inquiry. Breakthroughs do not occur in isolation or overnight, they arise from sustained engagement, careful reasoning, and a willingness to challenge assumptions. Planck's work reminds us that the frontiers of knowledge often lie where observation and theory diverge, where anomalies beckon the curious, and where disciplined imagination can illuminate the hidden structures of reality. His insight into quantized energy, born from the problem of blackbody radiation, would transform physics forever, demonstrating the profound impact of a single, well-conceived idea pursued with dedication and rigor. Planck's journey through the blackbody problem exemplifies how careful attention to nature's subtle clues can lead to revolutionary understanding. It illustrates that the universe is often more intricate than first appearances suggest, and that persistent inquiry, guided by both reason and creativity, can reveal principles that transform our comprehension of reality. Through the quantum hypothesis, Planck not only solved a long-standing scientific puzzle, but also provided the conceptual key that unlocked the quantum universe, forever altering humanity's view of the microscopic world. The late 19th century was a time of confidence in classical physics, a period when Newtonian mechanics and Maxwell's theory of electromagnetism seemed to explain nearly every natural phenomenon. Yet, beneath this apparent certainty, subtle anomalies were beginning to emerge, puzzles that defied conventional explanations. Among the most significant of these was the problem of blackbody radiation, which Max Planck had addressed through his radical idea that energy is quantized. What began as a solution to a technical problem soon evolved into a conceptual revolution, laying the foundation for quantum theory, a framework that would fundamentally transform our understanding of the universe. Quantum theory emerged not from a single moment of inspiration, but from a gradual accumulation of insights and observations. Planck's introduction of quantized energy in 1900 marked the first step, but the implications of this discovery extended far beyond thermal radiation. The concept challenged centuries of scientific thought, which had assumed that energy and matter were continuous, smoothly flowing, and infinitely divisible. By suggesting that energy could only exist in discrete packets, Planck fundamentally altered the way scientists conceptualized physical reality. This revolutionary shift did not occur in isolation. It was nurtured by a convergence of experimental anomalies, mathematical reasoning, and philosophical reflection. The early development of quantum theory was shaped by the interplay between empirical observation and theoretical imagination. Planck's radiation law provided a precise match to experimental data, resolving the ultraviolet catastrophe and demonstrating the utility of energy quantization. Yet, the full significance of this approach was not immediately apparent. For Planck, the quantum hypothesis was initially a formal tool, a convenient mathematical construct to reconcile theory with observation. It was only gradually that he, and the broader scientific community, began to appreciate that this hypothesis revealed something profound about the nature of reality itself, that at microscopic scales, energy and matter obeyed rules that were discrete, probabilistic, and fundamentally different from the smooth, deterministic laws of classical physics. One of the earliest extensions of Planck's ideas came from Albert Einstein, who, in 1905, applied the concept of quantized energy to explain the photoelectric effect. Einstein proposed that light itself consisted of discrete quanta, or photons, each carrying energy proportional to its frequency. This application of Planck's principle demonstrated that quantization was not limited to thermal radiation, but was a universal feature of nature. The photoelectric effect also revealed a deeper truth. The interaction between light and matter could not be fully explained by classical wave theory. This insight marked a critical step in the evolution of quantum theory, showing that discrete energy levels govern fundamental processes at the microscopic level. Niels Bohr further advanced the revolutionary nature of quantum theory through his model of the atom. By incorporating quantization into the orbits of electrons, Bohr explained the discrete spectral lines observed in hydrogen and other elements. His model demonstrated that electrons could occupy only certain energy levels, and that transitions between these levels involved the absorption or emission of discrete quanta of energy. Bohr's work highlighted the predictive power of quantum theory, providing an elegant framework that reconciled experimental observations with theoretical principles. The combination of Planck's initial quantization, Einstein's photon concept, and Bohr's atomic model illustrated how quantum theory began to coalesce into a coherent, though profoundly counterintuitive, framework for understanding nature. The revolutionary nature of quantum theory lies not only in its predictive accuracy, but also in its profound challenge to classical intuition. Classical physics had treated the world as continuous, deterministic, and predictable. In contrast, quantum theory introduced discreteness, probability, and uncertainty as fundamental aspects of reality. Planck's initial quantization of energy was the first hint of this radical shift. The subsequent work of Einstein, Bohr, and others extended the implications, revealing that at the atomic and subatomic levels, nature behaves according to rules that defy everyday experience. Electrons occupy specific energy levels, photons carry discrete energy, and measurement itself can influence outcomes. These principles shattered the classical view of an ordered, continuous universe and opened the door to a new understanding of reality. The birth of quantum theory also transformed the methodological foundations of physics. Scientists had traditionally relied on deterministic laws to describe the behavior of objects and predict future outcomes with certainty. Quantum theory introduced a probabilistic framework where predictions could only specify the likelihood of different outcomes. This shift required a reevaluation of long-standing assumptions about causality and the nature of scientific explanation. Planck's initial insight into quantized energy thus catalyzed a broader intellectual transformation, compelling physicists to rethink not only the specific behavior of heat and light, but also the fundamental principles underlying all physical processes. Planck's contribution to the birth of quantum theory exemplifies the delicate balance between empirical rigor and imaginative speculation. He was meticulous in analyzing experimental data and cautious in formulating theoretical hypotheses, yet he demonstrated a capacity to entertain ideas that challenged established norms. This combination of precision and creativity allowed him to introduce a revolutionary concept while maintaining credibility within the scientific community. It is a reminder that scientific revolutions often arise not from reckless conjecture, but from disciplined exploration of anomalies, guided by both observation and reasoning. The impact of quantum theory on subsequent scientific developments cannot be overstated. The framework introduced by Planck and extended by his successors provided the conceptual foundation for understanding atomic structure, chemical reactions, solid-state physics, and particle behavior. It enabled the development of technologies that have transformed modern life, including semiconductors, lasers, nuclear energy, and quantum computing. Every application of these technologies traces its conceptual roots to Planck's insight that energy is quantized, highlighting the practical as well as theoretical significance of the quantum revolution. The revolutionary nature of quantum theory also lies in its philosophical implications. By introducing discreteness and probability into the fundamental description of nature, it challenged deeply held assumptions about determinism and causality. Classical physics had depicted a universe governed by precise, predictable laws, where the future could, in principle, be deduced from complete knowledge of the present. Quantum theory suggested instead a universe in which uncertainty and probabilistic outcomes are intrinsic features. Planck's work, while initially focused on a specific problem in thermal radiation, planted the seeds for this profound reconceptualization of reality. Planck's intellectual approach during this period exemplifies the qualities that define transformative scientific thinkers. He combined careful observation, rigorous mathematical analysis, and creative imagination to tackle problems that others had considered intractable. He exhibited patience, resilience, and humility, recognizing the provisional nature of hypotheses and the importance of empirical validation. These qualities allowed him to navigate the uncertainty and skepticism that often accompany revolutionary ideas, gradually gaining acceptance for concepts that would ultimately reshape the foundations of physics. The revolutionary nature of quantum theory also lies in its capacity to unify diverse phenomena under a coherent framework. Planck's quantization of energy explained blackbody radiation, Einstein's photons explained the photoelectric effect, and Bohr's atomic model explained discrete spectral lines. These seemingly unrelated phenomena were connected by the principle of quantized energy, demonstrating the explanatory power of the emerging quantum framework. This unification highlights the profound conceptual shift initiated by Planck. By rethinking the nature of energy, he enabled a new understanding of matter, light, and the fundamental interactions that govern the universe. Quantum theory also challenged the boundaries of human intuition. While classical physics aligned closely with everyday experience, quantum phenomena often defy common sense. Particles exhibit both wave-like and particle-like behavior, energy exchanges occur in discrete units, and measurement affects outcomes. Planck's initial insight into quantized energy set the stage for these counterintuitive revelations, illustrating that nature operates according to principles that may appear strange yet are internally consistent and empirically verifiable. This realization underscores the revolutionary character of quantum theory. It reshapes not only scientific knowledge but also the very way we conceptualize reality. The birth of quantum theory marked a turning point in the history of science. It demonstrated that careful observation of anomalies, coupled with imaginative theoretical innovation, can lead to transformative understanding. Planck's insight, born from the problem of blackbody radiation, catalyzed a conceptual revolution that challenged classical assumptions, introduced probabilistic reasoning, and revealed the discrete nature of energy. The subsequent work of Einstein, Bohr, and countless others extended and refined these ideas, creating a comprehensive framework that underpins modern physics. Planck's pioneering work also exemplifies the human dimension of scientific discovery. He was not motivated by fame or recognition, but by a deep curiosity and a commitment to understanding the natural world. He faced skepticism, uncertainty, and the challenge of communicating revolutionary ideas to a conservative scientific community. Yet his persistence, humility, and intellectual rigor allowed him to introduce a concept that would transform our understanding of the universe. The birth of quantum theory thus reflects not only the power of ideas, but also the character of the thinker who brings them into being. The revolutionary nature of quantum theory is further evident in its long-term impact on scientific inquiry. It expanded the scope of physics to include phenomena previously considered inexplicable, from atomic spectra to subatomic interactions. It required the development of new mathematical tools, new experimental techniques, and new philosophical frameworks for interpreting reality. Planck's insight into quantized energy was the catalyst for this transformation, demonstrating how a single, well-conceived idea can generate far-reaching consequences for science and human understanding. Planck's contribution to the birth of quantum theory also highlights the iterative nature of scientific progress. The quantum hypothesis did not emerge fully formed. It developed through a process of careful observation, theoretical reflection, and continuous refinement. Planck's ability to navigate uncertainty, integrate empirical evidence, and propose a bold yet defensible hypothesis exemplifies the methodological rigor that underpins transformative science. His work demonstrates that revolutionary discoveries often arise from the meticulous combination of creativity, discipline, and sustained engagement with the natural world. By the end of this formative period, quantum theory had begun to assert its revolutionary character. It challenged classical assumptions, unified diverse phenomena, introduced probabilistic reasoning, and expanded the conceptual and technological horizons of physics. Planck's pioneering insight into quantized energy served as the cornerstone of this transformation, demonstrating that careful observation, rigorous analysis, and imaginative speculation can illuminate aspects of reality that were previously hidden from view. The birth of quantum theory thus represents both a conceptual revolution in science and a testament to the power of disciplined curiosity and intellectual courage. Planck's work on the birth of quantum theory reminds us that the progress of science is both cumulative and revolutionary. It builds upon existing knowledge while simultaneously challenging assumptions and expanding conceptual frameworks. By introducing the idea of quantized energy, Planck catalyzed a shift that not only resolved specific experimental problems, but also transformed our understanding of the fundamental nature of reality. His contributions exemplify the qualities of a revolutionary thinker: intellectual rigor, imaginative insight, methodological discipline, and a persistent commitment to uncovering the hidden principles of nature. As the quantum hypothesis gained traction, the revolutionary nature of this new framework became increasingly apparent. Max Planck's initial insight into energy quantization, born from the problem of blackbody radiation, had opened a conceptual doorway that fundamentally altered physics. The early 20th century saw a cascade of discoveries, each reinforcing the idea that the microscopic world operates according to principles that defy classical expectations. Electrons, photons, and atomic energy levels all exhibited behaviors that could only be understood within a quantized framework. Planck's insight had not only resolved a technical problem, but had initiated a paradigm shift, demonstrating that reality at its most fundamental level is discrete, probabilistic, and profoundly different from everyday experience. Albert Einstein's extension of Planck's ideas into the photoelectric effect exemplified this revolutionary trajectory. By proposing that light consists of discrete quanta, or photons, Einstein demonstrated that Planck's quantization principle was not limited to thermal radiation, but was a universal feature of nature. The photoelectric effect revealed that light interacts with matter in discrete, quantifiable amounts, a phenomenon inexplicable by classical wave theory. This discovery validated Planck's concept of energy quanta and extended its implications, establishing the universality of quantization and showing that fundamental interactions themselves are governed by discrete exchanges of energy. The revolutionary nature of quantum theory was further highlighted by Niels Bohr's atomic model. By applying quantization to electron orbits, Bohr explained the discrete spectral lines observed in hydrogen and other elements. Electrons were no longer free to occupy arbitrary positions, they were confined to specific energy levels, transitioning between these levels through the absorption or emission of energy quanta. Bohr's model provided a concrete example of how Planck's abstract principle could explain tangible, observable phenomena. The success of Bohr's atomic theory illustrated that quantization was not merely a mathematical convenience, but a fundamental characteristic of nature. Reshaping the understanding of atomic structure and laying the groundwork for modern atomic physics, the implications of quantum theory extended beyond physics, challenging the philosophical assumptions that had guided scientific thought for centuries. Classical physics envisioned a universe governed by continuous, deterministic laws, where the future could be precisely predicted from knowledge of the present. Quantum theory introduced a radically different view. At microscopic scales, the world is governed by discrete units, probabilistic outcomes, and inherent uncertainties. Planck's quantization of energy revealed that the predictability and continuity of classical physics are approximations, valid only at macroscopic scales. At the atomic and subatomic levels, nature follows rules that are counterintuitive yet consistent, requiring a reimagining of fundamental concepts such as causality, determinism, and measurement. The development of quantum theory also transformed the methodology of physics. Scientists could no longer rely solely on deterministic equations, they needed probabilistic models, statistical methods, and new experimental approaches. Planck's work demonstrated the importance of integrating theory and experiment, of allowing anomalies to guide conceptual innovation. His careful analysis of blackbody radiation data, combined with imaginative theorizing, exemplified the process by which revolutionary scientific ideas emerge. This methodology, observing anomalies, formulating hypotheses, and iteratively refining models, is a hallmark of quantum theory and continues to guide research in physics today. Max Planck's approach to the birth of quantum theory reflects a profound balance between caution and creativity. While he introduced a radical idea, he did so with meticulous attention to empirical evidence and mathematical rigor. He framed his hypothesis in terms of observable phenomena, allowing the scientific community to engage with it critically. This balance enabled Planck to propose a concept that challenged classical norms without alienating the broader scientific establishment. His careful presentation ensured that the quantum hypothesis was taken seriously, paving the way for its extension by Einstein, Bohr, and others into a comprehensive framework for understanding the microscopic universe. Quantum theory's revolutionary impact is evident not only in its explanatory power, but also in its ability to unify diverse phenomena. Planck's quantization principle explained blackbody radiation, Einstein's photons explained the photoelectric effect, and Bohr's model accounted for atomic spectra. These seemingly unrelated observations were connected by the concept of discrete energy units, demonstrating the unifying potential of quantum theory. This unification underscored the conceptual leap initiated by Planck. By reconceptualizing energy as quantized, he provided a coherent framework capable of explaining multiple, previously puzzling phenomena, revealing deep patterns in nature that classical physics could not account for. The quantum revolution also challenged the limits of human intuition. Everyday experience suggests continuity, smoothness, and predictability, yet quantum phenomena often behave in ways that defy these expectations. Electrons display both particle-like and wave-like behavior, photons act as discrete packets of energy, and measurement itself influences outcomes. Planck's insight into quantized energy initiated this shift, demonstrating that rigorous reasoning, grounded in observation, can reveal truths that appear paradoxical from a classical perspective. The revolutionary nature of quantum theory lies in its ability to describe a universe fundamentally different from our intuitive experience, yet entirely consistent and empirically verifiable. Planck's contribution exemplifies the interplay between individual insight and collective scientific progress. While he introduced the quantum hypothesis, its implications were explored, extended, and validated by a generation of physicists who built upon his ideas. Einstein's photons, Bohr's atomic orbits, and subsequent developments in quantum mechanics illustrate how revolutionary concepts propagate through scientific discourse. Planck's careful, disciplined introduction of quantized energy created a foundation for this collaborative evolution, highlighting the cumulative and interconnected nature of scientific discovery. The birth of quantum theory also had profound technological implications. By understanding that energy is quantized, scientists could explore the behavior of electrons, photons, and atomic structures in unprecedented detail. This knowledge led to innovations such as semiconductors, lasers, nuclear energy, and, eventually, quantum computing. Each of these technologies traces its conceptual roots to Planck's initial insight, demonstrating the enduring practical significance of the quantum revolution. Beyond theoretical physics, Planck's work transformed human capability, enabling applications that have reshaped industry, communication, and everyday life. The philosophical dimensions of quantum theory are equally profound. By introducing discreteness, probability, and inherent uncertainty, the theory challenged assumptions about determinism and predictability. Planck's initial insight forced a revaluation of the relationship between observation, measurement, and reality. Classical physics treated the universe as an objective machine, predictable in principle. Quantum theory revealed a universe in which the observer plays an active role, where measurement affects outcomes, and where probabilities replace certainty. This philosophical shift, grounded in empirical observation and rigorous theory, exemplifies the revolutionary character of quantum theory, showing that scientific discoveries can reshape not only knowledge, but also our understanding of reality itself. Planck's work also highlights the iterative, cumulative nature of revolutionary science. The quantum hypothesis did not arise fully formed, but developed through careful observation, mathematical modeling, and theoretical reflection. Planck's patience, intellectual rigor, and willingness to challenge classical assumptions enabled him to navigate uncertainty and skepticism. This methodological discipline ensured that the quantum hypothesis would endure, evolve, and ultimately transform the foundations of physics, demonstrating that revolutionary discoveries often emerge from sustained inquiry and disciplined exploration rather than sudden flashes of insight. The revolutionary impact of quantum theory is further evident in its explanatory and predictive power. Planck's quantization resolved the ultraviolet catastrophe, Einstein's photons explained light-matter interactions, and Bohr's atomic model accounted for spectral lines. Subsequent developments, including Schrödinger's wave mechanics and Heisenberg's matrix mechanics, extended these principles to broader domains. Planck's initial insight provided the conceptual scaffolding for this expansion, illustrating how a single, well-conceived idea can catalyze an entire scientific revolution. Planck's approach also underscores the importance of intellectual humility and openness in transformative science. He recognized the provisional nature of his hypotheses, carefully framing his ideas to align with empirical data while remaining open to future refinement. This humility enabled him to introduce a concept that challenged established norms without provoking outright rejection, creating space for subsequent theorists to explore and extend the quantum framework. The birth of quantum theory, therefore, reflects not only conceptual innovation but also the character of the thinker, whose discipline, patience, and integrity fostered a revolution in understanding. Quantum theory also illustrates the interplay between abstract reasoning and concrete observation. Planck's derivation of quantized energy involved sophisticated mathematics, yet it was firmly grounded in experimental evidence from blackbody radiation. This integration of theory and observation exemplifies the scientific method at its most powerful, rigorous analysis guided by empirical reality, capable of revealing patterns and principles that are not immediately apparent. The revolutionary nature of quantum theory lies in this synthesis, demonstrating that profound insights emerge from the alignment of conceptual imagination with meticulous observation. By the conclusion of this formative period, quantum theory had established itself as a fundamentally new framework for understanding nature. Planck's quantization of energy, Einstein's photon theory, and Bohr's atomic model collectively transformed physics, introducing discreteness, probability, and uncertainty as central features of the microscopic world. This conceptual revolution reshaped not only scientific knowledge, but also the way humans perceive reality, challenging intuitive notions and opening new domains for exploration. Planck's insight into quantized energy thus represents the birth of a scientific revolution, one that continues to influence physics, philosophy, and technology to this day. The revolutionary character of quantum theory is evident in its enduring influence. It has reshaped scientific inquiry, enabling explanations for phenomena ranging from atomic structure to nuclear interactions. It has driven technological innovation, underpinning devices and systems that define modern life. It has challenged philosophical assumptions, inviting reconsideration of determinism, causality, and the role of observation in shaping reality. Planck's initial insight into energy quanta served as the catalyst for this transformation, demonstrating how a single conceptual innovation, grounded in empirical observation and rigorous reasoning, can redefine an entire field of knowledge. Through the lens of Planck's contribution, one can see that the birth of quantum theory exemplifies the essence of scientific revolution. It required courage to question established norms, creativity to imagine new possibilities, and discipline to ensure that insights were firmly grounded in observation and mathematics. Planck's quantization of energy solved a specific problem in thermal radiation, yet its implications reverberated across physics, technology, and philosophy. This transformative impact illustrates the power of disciplined curiosity and imaginative reasoning to reshape human understanding of the universe. As Max Planck continued to explore the mysteries of energy and radiation, he realized that his revolutionary idea, the quantization of energy, required a fundamental parameter to connect the discrete packets of energy to observable phenomena. This parameter, now famously known as Planck's constant, would become one of the most significant and enduring contributions to physics. Planck's constant represented a bridge between the abstract world of theoretical reasoning and the tangible results of experimental observation. It was a tiny number, yet it encapsulated the profound principle that energy is not continuous but occurs in discrete, indivisible units proportional to the frequency of radiation. This simple proportionality would become a cornerstone of modern physics, influencing the development of quantum theory and reshaping our understanding of the microscopic universe. Planck introduced the constant while deriving his blackbody radiation law, a formula that described the intensity of radiation emitted by an idealized body at different frequencies and temperatures. Classical physics had failed spectacularly to explain this phenomenon, particularly at high frequencies, leading to the so-called ultraviolet catastrophe. Planck's solution involved an audacious leap. He proposed that energy is exchanged in discrete amounts, Tharpatchen, where E is the energy, where the frequency, and h Planck's constant. This equation was deceptively simple, yet it carried enormous conceptual weight. It implied that energy has a granular nature, fundamentally altering the framework through which scientists understood light, heat, and matter. The introduction of Planck's constant had immediate theoretical significance. It provided a precise quantitative measure for the energy of individual quanta, allowing physicists to calculate and predict experimental results with remarkable accuracy. For the first time, the discrepancy between classical predictions and observed blackbody radiation spectra was resolved. The constant h became a universal parameter, appearing wherever quantum effects were relevant, from the energy levels of atoms to the behavior of electrons in solids. Its universality underscored the radical implication of Planck's work. The laws of nature at the microscopic scale are quantized, and this quantization is governed by a constant that bridges the abstract and the observable. Planck's constant also had profound implications for the emerging field of quantum mechanics. It set the scale at which quantum effects become significant, marking a departure from the continuous, deterministic world described by classical physics. Phenomena that were previously inexplicable, such as the discrete spectral lines of hydrogen or the photoelectric effect, could now be understood through the lens of quantized energy. The constant provided the mathematical foundation for Einstein's explanation of the photoelectric effect, Bohr's model of the atom, and later, the formulation of wave mechanics and matrix mechanics. It was the thread that connected Planck's initial insight to the broader edifice of quantum theory, revealing a hidden structure underlying the behavior of light and matter. Beyond its role in theory, Planck's constant symbolized a paradigm shift in scientific thought. The recognition that energy is quantized forced physicists to rethink the fundamental assumptions of classical mechanics. Determinism and continuity were no longer absolute. The universe at its smallest scales operated according to rules that combined probability, granularity, and measurement-dependent outcomes. Planck's constant, though small in magnitude, became the emblem of this new worldview, a reminder that the microscopic realm is governed by principles that differ radically from those of the macroscopic world we experience daily. The influence of Planck's constant extended into experimental physics as well. It allowed scientists to design experiments that directly tested quantum predictions, providing empirical validation for theoretical models. For example, the measurement of electron energy levels, the behavior of photons in the photoelectric effect, and the quantization of angular momentum in atoms all relied on precise knowledge of h. The constant became a tool for bridging theory and experiment, enabling physicists to explore the quantum world with confidence and precision. Planck's constant also shaped the philosophical interpretation of physics. By introducing a fundamental unit of action, Planck challenged notions of continuous determinism and opened the door to probabilistic reasoning. Concepts such as wave-particle duality, the uncertainty principle, and the probabilistic interpretation of quantum mechanics all trace their origin, directly or indirectly, to h. It serves as a reminder that nature is discrete at its core, and that even seemingly smooth phenomena are composed of fundamental quanta. This understanding not only transformed physics, but also influenced broader philosophical perspectives on reality, causality, and the limits of human knowledge. Moreover, Planck's constant has enduring practical significance. It underpins technologies that define modern life, including semiconductors, lasers, magnetic resonance imaging, and quantum computing. Each of these applications relies on the quantized behavior of energy and the precise value of h to function. The constant, initially conceived as a solution to a theoretical puzzle, has become a fundamental building block for technological innovation, demonstrating the unexpected and far-reaching consequences of foundational scientific discoveries. Planck's careful introduction of his constant exemplifies his scientific temperament, cautious yet imaginative, rigorous yet visionary. He recognized the radical implications of quantization, but presented it as a solution to a specific problem, allowing the scientific community to engage with it systematically. Over time, as the significance of h became apparent, it transformed physics from a classical, deterministic discipline into a quantum science capable of explaining phenomena that had previously seemed mysterious or paradoxical. The constant thus represents both a specific numerical value and a profound conceptual shift, embodying the birth of a new understanding of nature. In reflecting on the significance of Planck's constant, one appreciates its dual role. It is both a practical tool for calculation and a symbol of the quantum revolution. It marks the boundary between classical and quantum physics, the scale at which new rules govern energy, matter, and the interactions between them. Its discovery exemplifies the power of careful observation, theoretical innovation, and disciplined imagination. Max Planck, through this singular contribution, provided humanity with a key to unlock the microscopic universe, demonstrating that even the smallest constants can carry the weight of the most profound transformations in science. Planck's constant remains a testament to the enduring impact of his work. It is invoked in nearly every discussion of quantum mechanics, a reminder of the shift from classical determinism to quantum reality. The constant connects phenomena as diverse as blackbody radiation, atomic spectra, the behavior of subatomic particles, and emerging quantum technologies. In this way, h serves as both a practical tool and a philosophical milestone, symbolizing the transition from a predictable, continuous universe to one that is discrete, probabilistic, and infinitely more complex. Through the lens of Planck's constant, the magnitude of Max Planck's contribution becomes clear. He did not merely propose a solution to a technical problem. He introduced a principle that would redefine physics, influence technology, and reshape our understanding of reality itself. The constant he discovered, tiny in numerical value but enormous in significance, continues to guide scientific thought, reminding us that profound insights often emerge from careful attention to nature, rigorous analysis, and the courage to challenge the assumptions of the past. Max Planck's revolutionary work on quantized energy did not merely resolve a single problem in physics. It created the foundation for an entirely new way of understanding the universe. By introducing the concept that energy is not continuous but exists in discrete packets, Planck challenged centuries of classical thinking and laid the groundwork for the development of modern quantum mechanics. The implications of his discovery extended far beyond blackbody radiation, influencing subsequent generations of scientists and reshaping the conceptual framework of physics itself. This was not a sudden revolution but a gradual evolution, driven by the meticulous integration of theory, experiment, and insight into the behavior of nature at its most fundamental level. The immediate impact of Planck's work was most clearly seen in the behavior of light and atoms. By proposing that energy is quantized, he provided the key to understanding phenomena that had long defied classical explanation. Albert Einstein, for instance, applied Planck's concept to explain the photoelectric effect, demonstrating that light behaves as discrete photons rather than a continuous wave. This extension of Planck's principle revealed that quantization is a universal property of nature, influencing not only the emission of radiation but also the interactions between light and matter. Einstein's work highlighted the generative power of Planck's discovery, showing that a single conceptual innovation could illuminate multiple, previously mysterious phenomena. Niels Bohr's atomic model further exemplified the transformative impact of Planck's discoveries. By applying the principle of energy quantization to electron orbits, Bohr explained why atoms emit and absorb light only at specific wavelengths. Electrons were no longer free to occupy any arbitrary energy level, they were confined to discrete orbits, transitioning between them through the absorption or emission of quanta of energy. Bohr's success demonstrated that Planck's seemingly abstract concept had tangible, observable consequences, providing a framework that could predict and explain experimental data with unprecedented accuracy. This development marked a critical step in the birth of quantum mechanics, showing how Planck's ideas could be extended and applied to a broader range of physical systems. The discoveries of Planck, Einstein, and Bohr collectively transformed the methodology of physics. Classical approaches, which assumed continuity and determinism, proved inadequate for explaining microscopic phenomena. Quantum mechanics introduced a new framework that incorporated probability, discreteness, and uncertainty as fundamental features of nature. Planck's constant became the central parameter in this framework, governing the scale at which quantum effects manifest. By providing a precise, quantifiable measure of energy quanta, Planck enabled scientists to move from qualitative speculation to quantitative prediction, bridging the gap between theory and experiment. Planck's contributions also encouraged the development of new mathematical tools and techniques. To describe the behavior of particles and energy at the quantum level, physicists had to move beyond classical equations, inventing formalisms such as matrix mechanics and wave mechanics. Schrödinger's wave equation, Heisenberg's matrix mechanics, and Dirac's quantum algebra all relied on the principles introduced by Planck, particularly the idea that energy and action are fundamentally quantized. These mathematical innovations allowed scientists to model atomic and subatomic systems with unprecedented precision, opening new horizons in both theoretical understanding and practical application. The pathway from Planck's initial insight to full quantum mechanics illustrates the cumulative and collaborative nature of scientific progress. Planck himself introduced the idea of quantized energy cautiously, framing it as a solution to a specific experimental problem. Subsequent thinkers, inspired by his hypothesis, extended, generalized, and formalized these concepts, creating a comprehensive theory capable of explaining a vast array of physical phenomena. This evolution demonstrates that revolutionary discoveries often begin with a single insight, but their full significance emerges through iterative refinement, dialogue, and experimentation across generations of scientists. Planck's discoveries also had profound philosophical implications. By establishing that energy is quantized, he challenged the deterministic worldview that had dominated science since Newton. In the quantum framework, certainty is replaced by probability, continuity by discreteness, and predictability by statistical outcomes. These principles forced a reevaluation of fundamental assumptions about reality, causality, and the limits of human knowledge. Planck's work thus not only transformed physics, but also reshaped the way humans conceptualize the natural world, bridging the gap between empirical observation and philosophical inquiry. The influence of Planck's discoveries extends into modern technology. Semiconductors, lasers, magnetic resonance imaging, and quantum computing all rely on the principles of energy quantization and quantum mechanics that emerged from his initial insight. The practical applications of his work illustrate the profound connection between foundational scientific theory and technological innovation. A discovery motivated by curiosity and intellectual rigor eventually enabled advances that shape everyday life, demonstrating the enduring relevance of Planck's contributions to both science and society. Planck's approach exemplified the qualities that define transformative scientific work: careful observation, disciplined reasoning, and the courage to challenge established assumptions. He navigated skepticism and uncertainty with patience, presenting a radical idea in a way that encouraged serious engagement rather than outright rejection. This combination of rigor and vision ensured that his insights could serve as a foundation for further exploration, ultimately enabling the creation of a comprehensive, predictive, and empirically validated framework for understanding the quantum world. By establishing the principle of energy quantization, Planck effectively laid the cornerstone for modern quantum mechanics. His discoveries demonstrated that seemingly minor anomalies, like the failure of classical physics to explain blackbody radiation, can signal the need for profound conceptual shifts. The framework he introduced allowed subsequent scientists to reinterpret a wide range of phenomena, from atomic spectra to particle interactions, and to predict outcomes that had previously been inaccessible. The revolutionary power of Planck's work lies not only in its explanatory success, but also in its ability to open new pathways for discovery, reshaping the trajectory of physics for the 20th century and beyond. In summary, Max Planck's discoveries paved the way for modern quantum mechanics by introducing the principle of quantized energy, providing a universal constant to govern microscopic phenomena, and inspiring subsequent scientists to extend these insights into a comprehensive theoretical framework. His work transformed both the conceptual and practical landscape of physics, demonstrating the power of careful observation, imaginative reasoning, and disciplined inquiry. Through his pioneering efforts, Planck not only solved a pressing problem in thermal radiation, but also unlocked a new realm of understanding, laying the foundation for a science that continues to reveal the profound and intricate nature of the universe. Max Planck's work fundamentally reshaped the landscape of physics, leaving a legacy that extends far beyond his own time. By introducing the concept of energy quantization, he not only resolved the long-standing problem of blackbody radiation, but also laid the foundation for the development of modern quantum mechanics. The significance of his discoveries cannot be overstated. They transformed the way scientists understand the microscopic world and provided the conceptual framework upon which the entirety of quantum theory was built. Planck's insights established principles that continue to guide research, influence technological innovation, and shape our understanding of the universe to this day. Planck's legacy is evident in the breadth and depth of scientific progress that followed his pioneering work. The introduction of quantized energy opened the door for the development of atomic models, beginning with Niels Bohr's successful explanation of hydrogen's spectral lines. By applying Planck's constant and the principle of discrete energy levels, Bohr demonstrated that electrons occupy specific orbits and transition between them by absorbing or emitting quanta of energy. This breakthrough provided tangible, observable confirmation of Planck's ideas, showing that the microscopic world operates according to rules that are fundamentally different from those described by classical physics. The influence of Planck's discoveries extended rapidly through the early 20th century, as Albert Einstein applied the concept of energy quanta to explain the photoelectric effect. By proposing that light itself is composed of discrete photons, Einstein provided a powerful example of how Planck's principle could unify diverse physical phenomena. This application not only reinforced the validity of Planck's quantization, but also demonstrated the generative potential of his ideas, showing that a single conceptual breakthrough could illuminate multiple, previously inexplicable aspects of nature. Einstein's work would ultimately earn him a Nobel Prize, yet it remained deeply rooted in Planck's initial insight, exemplifying the enduring reach of Planck's legacy. Planck's influence also extended to the philosophical foundations of physics. Classical mechanics had assumed a continuous, deterministic universe, but the advent of quantum theory revealed a fundamentally different reality. Energy quantization, the discrete nature of photons, and the probabilistic behavior of subatomic particles all challenged long-standing assumptions about causality, predictability, and the nature of physical law. Planck's work forced a re-evaluation of these principles, demonstrating that the universe at its most fundamental level is governed by rules that diverge significantly from everyday intuition. In doing so, Planck helped usher in a new era of scientific thinking, one in which observation, measurement, and probability play central roles. The enduring legacy of Planck's discoveries is also evident in the methodologies and approaches that they inspired. By demonstrating the need to reconcile experimental anomalies with theoretical reasoning, Planck emphasized the importance of integrating empirical evidence with conceptual innovation. His careful analysis of blackbody radiation, combined with the audacious introduction of quantized energy, exemplifies the scientific method at its most powerful, a process in which observation, hypothesis, and mathematical rigor converge to reveal fundamental truths. This approach has become a cornerstone of modern physics, guiding research in quantum mechanics, particle physics, and beyond. Technological advancements provide another tangible dimension of Planck's legacy. The principles he introduced underpin a wide range of modern innovations, from semiconductors and lasers to nuclear energy and quantum computing. Each of these technologies relies on the quantization of energy, the behavior of electrons in discrete states, and the probabilistic rules of quantum mechanics. The practical applications of Planck's work illustrate the profound impact that foundational scientific discoveries can have on society, demonstrating that theoretical insights often lay the groundwork for technological revolutions that transform daily life. Planck's influence also extends to subsequent generations of physicists, many of whom regarded him as both a mentor and an inspiration. The quantum revolution, fueled by his ideas, attracted some of the greatest minds in physics, including Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. These scientists expanded upon Planck's principles, developing matrix mechanics, wave mechanics, and relativistic quantum theories that collectively constitute the modern framework of quantum mechanics. Through their work, Planck's initial insight into quantized energy became the foundation for a vast and ever-expanding domain of scientific exploration, illustrating how one discovery can catalyze decades of intellectual progress. Planck's legacy is not solely technical, it is also deeply human. He approached scientific challenges with patience, humility, and rigorous attention to detail. He introduced revolutionary ideas cautiously, ensuring they were grounded in empirical observation and mathematical consistency. His ability to balance creativity with discipline allowed him to propose concepts that challenged established norms while maintaining credibility within the scientific community. This combination of intellectual courage and methodological rigor has become a model for scientific inquiry, demonstrating that groundbreaking discoveries often require both bold vision and meticulous reasoning. The philosophical and cultural impact of Planck's work is equally notable. By demonstrating that the universe is quantized at its most fundamental level, he contributed to a broader understanding of nature as complex, layered, and often counterintuitive. Quantum theory, emerging from his discoveries, has influenced not only physics but also philosophy, computing, information theory, and even artistic and literary conceptions of reality. Planck's ideas challenge humanity to reconsider the limits of knowledge and the assumptions underlying perception, highlighting the profound ways in which scientific insights can reshape thought and culture. Planck's constant, introduced as a seemingly abstract parameter in the solution to the blackbody problem, remains a central element of physics. It governs the scale at which quantum effects dominate, linking energy and frequency, and appears in equations describing phenomena from atomic transitions to quantum tunneling. The constant serves as both a practical tool for calculations and a symbolic representation of the shift from classical to quantum thinking. Its continued relevance underscores the lasting power of Planck's discoveries, demonstrating that foundational scientific principles can endure across generations, forming the backbone of both theory and application. Ultimately, Max Planck's legacy is measured not only by the specific discoveries he made, but also by the profound transformations they enabled. His introduction of energy quantization reshaped scientific understanding, inspired technological innovation, and opened new avenues of inquiry that continue to expand the boundaries of human knowledge. From the behavior of subatomic particles to the development of quantum computing, Planck's work resonates through both the intellectual and practical realms, illustrating the enduring significance of fundamental scientific insight. Through careful observation, disciplined analysis, and imaginative reasoning, Planck revealed a universe far richer and more intricate than classical physics had imagined. His discoveries serve as a testament to the transformative power of ideas, demonstrating that even a single conceptual breakthrough can alter the trajectory of science, technology, and thought. The legacy of Max Planck endures not merely in equations or constants, but in the ongoing quest to understand the quantum universe he helped unveil, inspiring generations of scientists to explore, question, and uncover the hidden structures of reality. Max Planck's contributions to physics transcend his own lifetime, leaving a legacy that continues to shape the modern scientific world. By introducing the concept of energy quantization, he opened the door to the revolutionary field of quantum mechanics, transforming the way humanity understands the universe at its most fundamental level. The implications of his work are vast, influencing not only theoretical physics but also technology, philosophy, and the broader perception of nature itself. Planck's insights revealed that the microscopic world operates according to rules that differ profoundly from everyday experience, challenging centuries of classical thinking and reshaping the trajectory of scientific discovery. The discovery of quantized energy marked a turning point in physics. Before Planck, classical theories assumed that energy varied continuously, but experimental anomalies, such as the failure to explain blackbody radiation, suggested that a deeper principle was at work. Planck's introduction of energy quanta provided a solution that reconciled theory and observation, demonstrating that energy is exchanged in discrete amounts. This principle not only resolved long-standing problems, but also laid the groundwork for the development of quantum theory, influencing every subsequent investigation into atomic and subatomic phenomena. Planck's work directly inspired a generation of scientists who would expand upon his discoveries, building the edifice of modern quantum mechanics. Albert Einstein applied Planck's principle to explain the photoelectric effect, revealing that light itself behaves as discrete photons. Niels Bohr used quantization to develop his atomic model, accurately predicting the behavior of electrons and the spectral lines of hydrogen. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac further extended these ideas, formulating mathematical frameworks that describe the behavior of particles, waves, and fields in the quantum realm. Planck's insights served as the essential starting point for these developments, highlighting the enduring influence of his original discovery. The practical impact of Planck's work is equally remarkable. Quantum mechanics, grounded in the principles he introduced, underpins a wide range of modern technologies that shape everyday life. Semiconductors, which power computers and smartphones, rely on the behavior of electrons in discrete energy levels. Lasers, essential for communication, medicine, and industry, operate on the principle of quantized energy emission. Nuclear energy, magnetic resonance imaging, and quantum computing all trace their conceptual roots to Planck's insight into the quantum nature of reality. These applications demonstrate how a theoretical breakthrough can yield transformative technological innovations, illustrating the profound and tangible effects of foundational scientific work. Planck's contributions also influenced the philosophical understanding of the universe. By revealing the discrete nature of energy and the probabilistic behavior of particles, he challenged classical assumptions about determinism, continuity, and causality. The quantum framework initiated by his work compels scientists and philosophers alike to reconsider the fundamental structure of reality. Questions about observation, measurement, and the limits of knowledge arise naturally from the principles he introduced, prompting a re-evaluation of how humans conceptualize the natural world. In this sense, Planck's legacy extends beyond physics, shaping intellectual inquiry in multiple disciplines. The introduction of Planck's constant provided a tangible measure of the quantum world. This constant defines the scale at which quantum effects become significant, linking energy and frequency in a precise, predictable way. It appears in virtually every equation of quantum mechanics, from the energy levels of electrons to the behavior of photons. As both a practical tool and a symbolic representation of the quantum revolution, Planck's constant serves as a reminder of the radical conceptual shift he initiated. Its continued relevance underscores the enduring nature of his discoveries and their central role in modern science. Planck's legacy is also evident in the methodology of scientific inquiry. His approach combined meticulous observation, mathematical rigor, and imaginative reasoning. By carefully analyzing experimental anomalies and proposing a hypothesis that challenged classical assumptions, he exemplified the process by which revolutionary ideas emerge. His work demonstrates that scientific breakthroughs often arise from a careful balance of creativity and discipline, highlighting the human qualities that underpin transformative discoveries. Future generations of scientists have drawn inspiration from Planck's method, applying similar principles in the pursuit of new knowledge across diverse fields. The cultural and educational impact of Planck's work should not be underestimated. Quantum mechanics, initiated by his discoveries, has become a central subject in physics education, shaping the training of scientists worldwide. Textbooks, lectures, and research programs all trace their foundations to the principles he introduced. Beyond education, Planck's story exemplifies the power of curiosity, perseverance, and intellectual courage, serving as an inspiration for anyone seeking to explore the unknown and expand the boundaries of human understanding. Max Planck's influence is also evident in the collaborative nature of modern science. While he initiated the quantum revolution, subsequent scientists built upon his insights, creating a dynamic interplay of ideas that continues today. This progression illustrates how foundational discoveries can catalyze decades of cumulative knowledge, with each generation extending and refining the work of its predecessors. Planck's discoveries thus serve as a cornerstone of scientific progress, demonstrating that transformative ideas can ripple through time, influencing both theory and practice long after their inception. In reflecting on Planck's enduring impact, it is clear that his work transformed both the conceptual and practical landscape of physics. By uncovering the quantum nature of energy, he revealed a hidden structure within reality, providing the framework for understanding atoms, molecules, and subatomic particles. His discoveries enabled technological innovations that have revolutionized modern life and challenged philosophical assumptions about determinism and reality. The principles he introduced continue to guide research in quantum physics, cosmology, information theory, and emerging fields such as quantum computing, highlighting the lasting relevance of his work. Ultimately, Planck's legacy is a testament to the power of human curiosity and intellectual perseverance. He demonstrated that careful observation, rigorous analysis, and the courage to question established assumptions can lead to profound insights about the universe. His work transformed the way humanity understands the natural world, inspiring generations of scientists to explore, experiment, and expand the boundaries of knowledge. The quantum universe he helped reveal continues to fascinate, challenge, and inspire, a lasting monument to his genius and vision. Through the lens of history, Max Planck stands as one of the pivotal figures in science, whose discoveries not only solved specific problems but also fundamentally reshaped the trajectory of human understanding. His work exemplifies the enduring impact of foundational scientific insight, showing how a single revolutionary idea can influence theory, technology, philosophy, and culture. In unveiling the quantum universe, Planck left an indelible mark on the world, a legacy that continues to illuminate the hidden structures of reality and guide humanity's quest for knowledge.